Every day, millions step onto escalators without a second thought. To most, they're just moving stairs, a background convenience of city life. But beneath that smooth motion lies an incredible story of precision engineering, mechanical mastery, and human-centered design. From roaring motors hidden deep below to perfectly synchronized steps and handrails, escalators are far more than they appear. In this video, we lines peel back the layers of this overlooked marvel and reveal the extraordinary systems that keep urban life in motion. Welcome to Civil Engineering Edge, and this is Escalator Secrets, Beyond the Moving Stairs design, where the familiar becomes fascinating. Ever wondered what really goes on beneath your feet when you step onto an escalator? It seems so simple, yet there's a hidden world of complex engineering at play. Get ready to have your mind blown as we unveil the ingenious secrets behind these everyday moving stairs, revealing how they flawlessly transport millions every single day. The illusion of simplicity, visuals, a mesmerizing sequence of escalators from different perspectives, aerial shots of shopping malls, subway stations, and airports with slow motion and time-lapse transitions. Every day, millions of people step onto escalators without giving them a second thought. They glide effortlessly from one level to another, chatting, scrolling on their phones, or gazing into space, completely unaware that they are standing on one of the most remarkable mechanical inventions ever designed. Escalators appear simple, a set of stairs that move. But behind that effortless motion lies an astonishingly intricate system of engineering precision and mechanical harmony. At its core, an escalator is more than a moving staircase. It's a continuous conveyor loop of steps, chains, gears, and tracks, all synchronized to perfection. What you see as individual steps are actually part of a single endless chain that cycles around to sprockets, one at the top and one at the bottom. Each step has two pairs of wheels, one on the upper track and another on the lower track, that guide it smoothly along a carefully designed pathway. This track system controls the step's angle, ensuring that while in motion, the treads remain perfectly horizontal for passengers' stability and comfort. Inside the escalator, the motion begins with an electric motor, usually located at the top, which powers the main drive shaft. This shaft turns the sprocket wheels, setting the entire step chain in motion. As the steps move upward, they spread apart to form the staircase. As they return down underneath, they collapse together, creating a compact, flat surface ready for the next cycle. This transformation happens seamlessly, so perfectly that most people never notice it. The handrail, too, isn't merely decoration. It's powered by a friction-driven system synchronized with the speed of the steps, ensuring your hand moves in perfect harmony with your body. The truss, the rigid structural frame that holds the entire escalator, acts as its backbone, carrying the load of the steps, passengers, and motor components. Every tiny part, from the brush guards to the comb plates at the landing, is designed to ensure safety, efficiency, and reliability. What makes escalators truly fascinating is how this highly complex machinery achieves such smoothness and silence that it almost hides its own complexity. That is the true illusion of simplicity, a perfect blend of mechanical precision, balance, and engineering artistry beneath our very feet. Do you ever wonder how these things really work? Visuals, animated cutaway of an escalator showing the step chain, drive motor, truss, and step return path. Let's look beneath the surface. Have you ever paused midway on an escalator ride and wondered, how does it stay so perfectly balanced? Why do the steps never tilt or slide apart? And how does this entire system keep working day after day, year after year, with such precision? The secret lies in the heart of the escalator, its step chain and track system. Each step is connected to the next through a continuous loop of linked chains that pass over sprockets at both ends. Every step has two sets of wheels. The upper wheels ride along the passenger track, while the lower wheels follow a separate path that adjusts the step's position. When the steps are on the visible section, these two tracks are parallel, keeping the treads perfectly level. But as they move underneath, the tracks separate, forcing the steps to collapse into a flat surface to complete the return loop. The drive motor, typically an induction motor of around 7.5 to 15 kilowatts, supplies the rotational force that turns the main drive shaft. Through a series of reduction gears, this motion is transferred to the step chain, converting electrical energy into controlled mechanical motion. The speed is carefully regulated, usually between 0.45 and 0.65 meters per second, ensuring both efficiency and safety for passengers. Equally fascinating is the synchronization between the handrail and the steps. The handrail is driven by a separate friction belt system powered by the same motor, adjusted to move at the same speed as the steps. This ensures the rider's balance and stability. Even a small difference in their relative speed could cause discomfort or accidents, which is why this synchronization is one of the most precisely tuned aspects of escalator design. Safety features are everywhere. Skirt brushes prevent clothing entrapment. COMB plate sensors detect foreign objects. And emergency stop buttons are placed at both landings. If anything disrupts normal operation, a jammed step, overspeed, or chain misalignment, the entire system stops instantly. Every mechanical part of an escalator, from the drive chains to the safety sensors, represents a deep understanding of load distribution, torque, friction, and material science. What seems like a simple glide upwards is actually a marvel of mechanical coordination, a perfect example of how civil and mechanical engineering work hand in hand to create motion that feels effortless yet operates with mathematical precision. Everywhere yet overlooked, the ubiquity of escalators' visuals. Escalators operating in major airports, subways, and commercial towers, engineers performing maintenance checks and installations. Escalators are so common that they've become invisible. We encounter them in shopping malls, airports, metro stations, and skyscrapers, always functioning, always reliable, and almost always taken for granted. But when viewed through the lens of engineering, they are silent heroes of urban mobility. They efficiently move people through vertical spaces, bridging architectural levels without waiting, queues, or fatigue. From a civil engineering standpoint, every escalator is a carefully coordinated structural and mechanical installation. It begins with the truss, the main framework that supports the moving steps and the load of passengers. The truss must fit precisely between two building levels, resting on upper and lower landings. Its alignment, inclination usually 30 or 35, and load-bearing capacity must all be verified before installation. A single error in angle or misalignment could affect step geometry or drive efficiency. The escalator's components, including the truss, drive unit, and control system, are pre-assembled in factories and transported as massive modules. During installation, civil engineers ensure that the foundation and support structures can bear both static and dynamic loads. These loads vary depending on passenger traffic, step width, and incline angle, requiring precise calculations and safety margins. Material choice plays a vital role too. Stainless steel is commonly used for the step treads and skirt panels because of its strength, corrosion resistance, and durability. The truss is made from welded steel sections capable of supporting thousands of kilograms in motion. The balustrades, crafted from tempered glass or steel panels, add both safety and aesthetic appeal to the structure. Modern escalators also embrace sustainability. Newer systems use energy-saving drives, motion sensors, and regenerative braking to reduce power consumption. When passenger flow is low, sensors can slow the escalator or even pause it, resuming instantly when someone steps on. Some systems feed recovered kinetic energy back into the electrical grid, improving building energy efficiency. What's fascinating is that despite all these advancements, the fundamental design of the escalator has remained nearly unchanged for over a century. This enduring reliability shows how timeless the core engineering principles are, combining balance, motion, safety, and structural design. The next time you glide upward, remember that beneath those polished metal steps is a living machine, a symphony of gears, trusses, and mechanical intelligence silently carrying the world forward, one step at a time. Beyond the visible, the mechanical heart, unveiling the hidden drive system, motors, gears, and chains. Visual, slow-motion reveal of the Escalator's underside, animated 3D cutaways showing the motor, gear train, and drive chains in motion. Hidden beneath the shiny metal steps and polished handrails lies the true powerhouse of every Escalator, its drive system. This is the beating heart that keeps millions of people moving effortlessly every single day. The Escalator's drive system combines motors, gears, and chains in a seamless mechanical orchestra designed for constant operation, minimal noise, and maximum reliability. At the top of most Escalators sits the main drive motor, usually an electric induction motor ranging from 7.5 kilowatts to 15 kilowatts, depending on the length, angle, and passenger capacity. This motor generates rotational energy that is transmitted through a reduction gearbox, which slows down the motor's high rotational speed while increasing torque. The gearbox output is then connected to the main drive shaft, a heavy steel axle that drives the sprocket wheels at the top. These sprockets engage directly with the step chains, converting rotational motion into the continuous linear movement that makes the steps rise and descend. Visual cue: highlight chain movement and torque transmission through gears. The design precision here is astonishing. The step chains are made of high-tensile steel links designed to handle continuous stress. These chains loop endlessly around the truss, guided by sprockets both at the top and bottom. Each link must fit perfectly into the sprocket teeth to prevent slippage, vibration, or misalignment. Even a millimeter of deviation could cause jerks or step irregularities, a serious hazard in passenger transport. To maintain smooth motion, lubrication systems automatically deliver oil or grease to the moving parts, reducing friction and wear. In modern Escalators, engineers often use frequency converters VFDIs to precisely control motor speed, ensuring gentle starts, stops, and energy efficiency. Noise reduction is also a vital design goal. To achieve this, rubber dampers, silent chain designs, and advanced bearing systems are used to minimize vibration. The entire drive system is housed within a motor room or enclosed casing at the upper landing to protect it from dust, moisture, and tampering. In essence, the Escalator's drive system is a masterpiece of continuous motion, a combination of electrical power, mechanical precision, and structural engineering that works invisibly to deliver perfect reliability. Every time those stairs begin to move, you're witnessing an extraordinary symphony of engineering perfection, silently humming beneath your feet. Be the ingenious step mechanism. How steps appear, flatten, and disappear approx. 450 words visual, transparent side view animation showing step transformation from flat chain loop to staircase formation and back. Narration: one of the most fascinating engineering wonders of the Escalator is its step mechanism, the secret behind how the moving stairs seem to magically appear, rise, flatten, and vanish without breaking rhythm. To the casual observer, it's seamless, but to an engineer, it's a brilliant display of synchronized mechanical geometry. Each step on an escalator isn't an independent object. It's part of an endless chain of linked steps, connected by axles and guided along to continuous steel tracks that run the length of the escalator. The upper set of wheels supports the tread, the part you stand on, while the lower set controls its angular position. When the escalator starts, the steps at the bottom begin to rise as the two tracks gradually separate. This change in track height causes each step to tilt into position, creating the visible staircase formation. The key to this transformation lies in maintaining parallelism, ensuring that each tread remains perfectly horizontal even as it ascends or descends. This is achieved by carefully spacing the tracks so that as the front wheel climbs higher, the rear wheel follows an exact counterpath, maintaining the step's level orientation. As the steps reach the top landing, the process reverses. The two tracks converge again, causing the steps to flatten and merge seamlessly into a continuous horizontal surface before disappearing underneath. This flattening is what allows passengers to safely step off without feeling a sudden drop or incline. Visual cue: zoom into step linkages flattening under comb plate. The steps themselves are cast from die-formed aluminum or stainless steel, chosen for strength, corrosion resistance, and lightness. Each tread's surface features grooves that interlock with the comb plates at both landings, reducing the risk of entrapment and improving safety. This continuous looping motion, from stair to flat chain and back again, happens thousands of times a day with almost no human intervention. It's a marvel of design symmetry and load distribution. The geometry must remain flawless under dynamic loads of varying passenger weights. Even small irregularities in wheel alignment, track spacing, or chain tension could disrupt the entire cycle. So next time you ride an escalator, take a moment to glance down. Beneath those simple-looking steps is a dynamic ballet of motion, a constantly cycling machine that combines balance, geometry, and rhythm in perfect harmony. Safety first, braking systems, handrail synchronization, and emergency stops, visual. Engineers testing escalator brakes and sensors, animations highlighting safety circuits and handrail systems. While escalators are designed for smoothness and comfort, their most critical engineering focus lies in safety. Every component, from the brakes to the handrail, is designed to protect passengers, ensure mechanical integrity, and prevent accidents under any circumstance. Let us uncover the unseen safety mechanisms that make escalators one of the safest forms of vertical transport in the world. The first and most vital safety feature is the braking system. Escalators use two types of brakes: the main drive brake and the auxiliary brake. The main brake, usually mounted on the motor shaft, activates automatically whenever power is cut off or the emergency stop is pressed. It holds the steps firmly in place, preventing backward movement. The auxiliary brake, located on the drive sprocket or main shaft, serves as a backup. It activates instantly if the main brake fails or the speed exceeds safe limits. Both brakes use electromechanical control systems with fail-safe designs, ensuring that loss of power triggers braking instead of disabling it. Visual cue: animation showing braking during sudden stop. The handrail system is another marvel of synchronized engineering. The handrail consists of a continuous loop made of rubber, fabric, and steel wire reinforcement. It moves along its own guide tracks, driven by a separate friction wheel connected to the same drive system that powers the steps. The challenge is to ensure that the handrail moves at precisely the same speed as the steps. Even a tiny difference can cause passengers to lose balance. Engineers use fine-tuned speed ratios and electronic synchronization systems to achieve perfect harmony. Safety doesn't end there. Comb plate sensors detect foreign objects trapped between the steps and combs, triggering an immediate stop. Skirt deflectors and brush guards prevent clothing or shoes from being caught. Step demarcation lines, typically painted yellow, guide foot placement. Modern escalators also include load sensors, speed governors, and anti-reversal devices to monitor performance in real time. All these systems are backed by emergency stop buttons located at both the upper and lower landings, giving users or maintenance staff immediate control in case of danger. Together, these safety systems form an invisible shield, a combination of mechanical intelligence, precision sensors, and redundancy. They ensure that even though escalators handle millions of rides every day, failures are incredibly rare. In engineering terms, the escalator is not just a machine of motion. It is a machine of trust designed with one purpose above all: to move people safely, silently, and reliably through the modern world. Segment 3. Designed for flow, the human element visual split screen showing a crowded metro station escalator versus a quiet mall escalator with overlay graphics showing flow rates and speed indicators. Escalators are more than mechanical transport systems. They're dynamic human flow machines. Every escalator you see in a metro, airport, or shopping mall is engineered not just for motion, but for movement efficiency. Behind their operation lies one of the most carefully studied aspects of civil and transportation engineering: passenger throughput, the number of people an escalator can carry safely per unit time. Passenger capacity depends on several variables: step width, speed, inclination, and passenger behavior. A standard escalator step is 600 millimeters wide, allowing one person per step. Larger escalators, like those in airports or metro stations, often use 800 millimeters or even 1,000 millimeters wide steps, accommodating to passengers side by side. Speed also plays a crucial role. Most commercial escalators operate between 0.45 and 0.65 meters per second, balancing comfort with safety. However, high-traffic areas like subway systems may use speeds up to 0.75 meters per second to improve capacity. Engineers use the formula: capacity equals speed times persons per step times 3,600. Step pitch, for instance. An escalator moving at 0.5 meters per second with a step pitch of 0.4 meters and one person per step can transport roughly 4,500 passengers per hour. In a busy transit hub, multiple escalators are often arranged side by side or in parallel systems to multiply this throughput, ensuring smooth crowd dispersion without congestion. Visual cue: animated charts showing throughput variations by speed and width, but numbers alone don't tell the full story. Engineers also study flow psychology, how people stand, walk, or hesitate. In many countries, cultural habits dictate stand on the right, walk on the left, while others stand uniformly. These patterns directly affect practical capacity, leading engineers to analyze movement data and adapt designs accordingly. Additionally, landing space design is critical. The entry and exit zones must be wide, flat, and free of obstacles to prevent passenger pileups, especially during rush hours. Civil engineers often design these zones with visual cues, floor markings, and rail placement to guide traffic flow naturally. In essence, optimizing escalator capacity is a delicate dance between engineering, mathematics, and human behavior. It's about predicting movement patterns, managing safety, and designing for comfort, all to ensure that the flow of people never feels like a rush, but like a smooth, effortless glide through space. The subtle psychology of speed and incline, why some feel faster or steeper than others. Visual: people on different escalators reacting differently. One slow and gentle, another steeper and seemingly faster. Have you ever stepped onto an escalator and felt like it was racing faster than usual, even though the actual speed was the same? Or maybe you've ridden one that seemed unusually steep or slow. That perception isn't an illusion. It is a carefully engineered blend of physics and psychological design. Escalator design goes far beyond mechanical movement. It subtly interacts with human perception. To key design parameters, speed and incline angle shape how passengers feel during the ride. Standard escalators are inclined at 30, while compact models may reach 35 in steeper environments like subway tunnels. This 5-degree difference may seem minor, but psychologically, it changes everything. When the incline steepens, passengers' line of sight narrows, increasing the sense of height and speed. Our brains subconsciously compare vertical and horizontal motion cues, so a steeper incline tricks the eye into perceiving faster motion, even at identical speeds. Similarly, an escalator in an open atrium feels slower because the surrounding space provides visual references, while one in an enclosed shaft feels faster due to the tunnel-like compression of sight lines. Speed perception also depends on handrail synchronization and vibration feedback. If the handrail moves slightly slower or faster than the steps, it creates a mismatch between visual and tactile senses, making riders feel uneasy. That's why escalator engineers precisely calibrate handrail velocity to match the steps within plus or minus 2%. Visual cue. Diagrams showing how angle and visual reference affect perceived speed. Engineers must balance comfort and efficiency. A slow escalator feels safe but may frustrate commuters. A faster one increases capacity but can cause dizziness, especially in elderly passengers. Through empirical studies, optimal speeds were found to be around 0.5 meters per second for general public use, ensuring stability while maintaining flow. Lighting and acoustics also play subtle roles. Brightly lit, open environments make escalators feel slower and safer. Dim or enclosed spaces enhance the sense of speed, which is why underground stations use strong lighting and color contrasts to counteract the psychological intensity of motion. So, when an escalator feels fast or steep, it's not random, it's a meticulously engineered experience. Designers and civil engineers work together to ensure that physical performance and human comfort merge seamlessly, turning mechanical movement into something that feels natural, balanced, and reassuringly human. Accessibility considerations, impact on stroller, wheelchair, and luggage users, visual close-ups of passengers with strollers and suitcases using escalators, transitions to accessibility symbols and elevator integration in transport hubs. In the modern world, true engineering excellence means inclusivity. While escalators are primarily designed for pedestrians, engineers must also consider the needs of people using strollers, heavy luggage, or mobility aids. Accessibility is not just a social responsibility, it is an integral part of modern civil design standards. Escalators, by their very nature, are not suitable for wheelchair users as the moving steps and gaps pose serious safety risks. However, engineers address this limitation by designing integrated accessibility systems, primarily elevators, ramps, and moving walkways strategically placed beside escalators. These allow individuals with mobility challenges to navigate the same spaces safely and conveniently. Still, escalators play a significant role in accommodating stroller and luggage users. For them, design modifications and safety measures are essential. Step demarcations, anti-slip grooves, and cone plate designs are standardized under international codes like EN 115 and ASME A 17.1 to minimize slippage. The skirt panel gap, often just for millimeters, prevents wheels or handles from getting caught, while brush guards offer an added layer of protection. Visual cue. Engineering diagrams showing step width and safety clearance zones. Civil engineers must also ensure adequate landing areas. These flat zones at the top and bottom must be large enough for passengers to stabilize before or after moving. In high-traffic environments like airports, additional signage, audible signals, and visual warnings alert passengers carrying heavy items to use alternate paths. Modern escalators also incorporate variable speed drives and motion sensors that slow the system when no passengers are present, allowing smoother, safer entry for those with strollers or luggage. Some advanced models, especially in airports and malls, feature extra-wide treads up to 1,000 millimeters, offering better stability for those managing large bags or carts. Beyond hardware, accessibility extends to design, layout, and human flow management. Building codes require clear sightlines, accessible signage, and barrier-free approaches around escalators to ensure that everyone, regardless of ability, can navigate confidently. Ultimately, the goal of accessibility design isn't just compliance, it's inclusion by design. Escalators, elevators, and walkways work as one system, ensuring that every user, from a hurried commuter to a parent with a stroller, experiences the same sense of safety, fluidity, and independence. That is the human side of engineering. where mechanical precision meets compassion and thoughtful design for all. Escalators of tomorrow. Innovation on the horizon: smart escalators, energy efficiency, predictive maintenance, and real-time monitoring in the modern era of urban infrastructure. Even something as seemingly mundane as an escalator is undergoing a technological transformation. Smart escalators represent the next evolutionary step in public transport convenience, focusing on three crucial pillars: energy efficiency, predictive maintenance, and real-time monitoring. Traditional escalators often operate at a fixed speed, running continuously regardless of passenger load. However, smart escalators are equipped with motion sensors and variable frequency drives VFDs that intelligently adjust speed or even shut down during periods of low traffic. For example, at midnight in a shopping mall, a smart escalator may automatically enter a low-power sleep mode, drastically reducing energy consumption. Beyond energy savings, predictive maintenance has revolutionized how facilities manage escalator uptime. Embedded sensors constantly monitor vibration levels, motor temperatures, and chain wear, feeding data to a centralized control system. Using AI algorithms and IoT integration, these systems can detect abnormalities before they escalate into mechanical failures, allowing technicians to replace components proactively. This not only ensures public safety, but also prevents costly downtime. Meanwhile, real-time monitoring connects escalators to digital dashboards, allowing remote access for engineers and maintenance personnel. Any fault, whether it's a motor overload or step misalignment, immediately triggers alerts. Some advanced models even provide augmented reality AR interfaces for technicians, overlaying maintenance data directly onto a live video feed of the escalator. The combined result is a smarter, safer, and more sustainable transport system that aligns with global smart city visions. The shift toward these intelligent systems demonstrates that even in familiar infrastructure, innovation never rests. As cities grow denser, smart escalators are set to become key players in creating energy-conscious, user-friendly, and data-driven urban environments. Futuristic concepts, spiral escalators, maglev systems, and modular designs for adaptability. The future of escalator design is not limited to mere efficiency, it's about reimagining form, movement, and adaptability. One of the most fascinating examples of futuristic innovation is the spiral escalator. First developed by Mitsubishi Electric, these mesmerizing curved escalators use specially designed step chains and guide rails that bend smoothly around a central axis. They save space in compact architectural layouts while adding a striking aesthetic appeal in luxury malls and futuristic airports. But even more radical ideas are emerging. Maglev escalators, inspired by magnetic levitation trains, could one day replace traditional chain-driven systems. These designs eliminate friction, offering near-silent operation, ultra-smooth motion, and drastically reduced maintenance. Imagine escalators that glide on magnetic fields, requiring minimal lubrication or mechanical contact, extending their lifespan and energy efficiency. Another forward-thinking innovation lies in modular escalator systems. These units can be assembled, extended, or reconfigured based on building requirements. For example, a temporary installation at an exhibition center could later be reassembled elsewhere, reducing waste and cost. Modular designs also allow escalators to adapt quickly to future technological upgrades, such as integrating AI-based monitoring systems or energy harvesting trends. Architects and civil engineers are increasingly viewing escalators as living components of infrastructure, dynamic elements that evolve with user needs and technological possibilities. As futuristic concepts transition from prototypes to mainstream adoption, the humble escalator may soon become one of the most adaptable, elegant, and forward-thinking engineering elements in modern architecture. The potential impact of AI and advanced sensors on escalator operation and safety. Artificial intelligence and sensor technology are transforming escalators into intelligent, self-regulating systems capable of learning, predicting, and preventing issues long before they occur. AI-driven escalators analyze enormous data sets from passenger flow patterns to vibration signals to optimize performance in real time. For example, during rush hours in metro stations, AI can automatically adjust escalator speed to increase passenger throughput, while during low traffic periods, it can reduce operational intensity to conserve energy. Advanced sensor networks, including LiDAR, ultrasonic detectors, and infrared cameras, continuously scan for anomalies. These sensors detect anything from loose clothing near the comb plate to unexpected obstructions on the steps. If a potential hazard is identified, the system can initiate an automatic slowdown or emergency stop, often faster than a human operator could react. Additionally, smart handrails embedded with pressure sensors ensure synchronization with step movement, preventing slippage and maintaining user stability. One of the most promising developments is the use of AI-based predictive analytics. By combining historical performance data with live sensor input, AI can accurately forecast when parts such as step chains or bearings are likely to fail, prompting maintenance crews before any incident occurs. Furthermore, machine learning algorithms continuously refine their accuracy, learning from each event to enhance future safety responses. In the near future, escalators may also integrate crowd analytics systems, adjusting operational parameters dynamically based on passenger density, age demographics, or mobility patterns. For instance, an escalator could automatically switch to slow mode during elderly commuting hours or high-speed mode in office rush hours. Through AI and advanced sensors, the escalator of tomorrow will no longer be a passive transport mechanism, but an intelligent, interactive, and self-protecting system redefining public safety and efficiency in vertical mobility. The unsung urban hero, reiterating the complexity beneath the surface and their vital role in modern cities, escalators are often overshadowed by grander engineering feats, bridges, skyscrapers, and high-speed trains, but their quiet efficiency makes them one of the most vital arteries of modern urban life. Each step you take on an escalator is supported by a symphony of gears, chains, motors, and sensors, all working in perfect harmony. Beneath that polished metal surface lies a precisely engineered system designed to handle thousands of passengers daily, often operating non-stop for years. Engineers meticulously calculate every element: the inclination angle, step depth, balustrade design, and motor torque. Even the handrail synchronization must be flawless to fast, and it feels unstable to slow, and passengers lose confidence. The challenge is not only to move people, but to do so smoothly, safely, and reliably across a range of environmental conditions, from freezing airports to humid metro stations. Escalators are more than transportation tools. They are connective pathways that shape how cities flow. In crowded urban hubs like Tokyo, London, and New York, they keep millions moving efficiently between transport levels, shopping centers, and office complexes. Without them, congestion would skyrocket and accessibility would suffer. Every design decision, right from the placement of entry points to the curvature of steps, reflects deep human understanding. Engineers must consider visibility, passenger psychology, and even the sound of motion. That subtle humming you hear isn't random, it is tuned to ensure users feel the rhythm of movement. So next time you glide effortlessly upward or downward, remember, beneath your feet is a living machine, one that works tirelessly, silently, and seamlessly to keep modern cities alive and connected. Be a quick montage of diverse escalator scenes worldwide, highlighting their global significance. 450 words. Imagine a cinematic montage sweeping across the globe: Tokyo's neon-lit metro stations, New York's subway tunnels, Dubai's glittering malls, and London's historic underground. Each frame showcases escalators as the invisible backbone of modern life. In airports, they link terminals across continents. In subways, they serve as arteries that carry humanity's pulse through the veins of concrete. In Hong Kong, escalators climb steep hills, forming the world's longest outdoor escalator system. In Stockholm, engineers have installed climate-resistant escalators that brave the freezing Nordic winters. In India, sprawling metro networks have brought escalators to millions for the first time, transforming accessibility in both metropolitan and suburban regions. From the bustling corridors of Paris' Gare du Nord to the high-altitude rail stations of China's Chengdu, escalators demonstrate not only engineering excellence, but also cultural adaptation. Their design adapts to local architecture, footfall, and safety regulations, each version reflecting the unique character of the city it serves. These moving stairways are more than mechanical transport, they're symbols of progress. They represent humanity's constant desire to move upward, to connect spaces, and to bridge vertical divides. Each escalator tells a silent story of innovation meeting daily need, of engineers and architects working behind the scenes to shape our collective journey. When you observe them in different environments, curving spirals in luxury malls, transparent glass balustrades in futuristic airports, rugged industrial versions in metro tunnels, you see more than a machine. You see a global unifier carrying people of every background, language, and purpose up and down, every second, everywhere. The humble escalator may not demand attention, but its impact spans continents, making it one of civilization's most universal and democratic inventions. Next time you step on an escalator, you'll see it differently, won't you? Now that you've glimpsed the hidden marvels beneath those polished steps, every escalator ride will feel different. The next time you step onto one, pause for a moment, feel the hum of the motor beneath, the rhythmic alignment of the steps, and the perfect motion of the handrail beside you. What once seemed mundane now reveals a world of precision, purpose, and invisible brilliance. Escalators are more than just moving stairs, they are living monuments of engineering ingenuity. Every component, from the smallest bolt to the heaviest drive chain, tells a story of careful calculation and safety-focused design. Each step represents the silent work of countless civil, mechanical, and electrical engineers who ensure that something so ordinary remains extraordinarily reliable. The next time you glide upward in a busy shopping mall or descend into the depths of a subway, remember the intelligence behind it all, the power that drives millions safely every day. Think of the sensors that protect, the motors that sustain, and the innovations that keep evolving in silence. These machines don't just move people, they move societies forward. Escalators embody what engineering is truly about, making life effortless while hiding the complexity beneath beauty and function. They're proof that progress doesn't always roar, it often hums quietly beneath our feet. So yes, next time you step on an escalator, you'll see it differently, won't you? You'll see not just a staircase in motion, but a masterpiece of mechanical poetry, one that carries the world upward, step by step, day by day. From the bustling metros of Tokyo to the glittering malls of Dubai, escalators are the quiet heroes of modern cities, lifting humanity with every step. We often overlook them, yet they define the rhythm of urban life. Now that you know their secrets, you'll never ride them the same way again. This has been Civil Engineering Edge, where we uncover the hidden brilliance behind everyday structures. If you enjoyed this deep dive into the unseen world of escalator engineering, don't forget to like, share, and subscribe for more insightful videos on civil engineering wonders. Keep learning and keep building forward.